It's very much my pleasure to introduce Dr. Michael MacFerrin, who is currently a research scientist at NOAA. Hi, Mike. There you are. So just a brief introduction. He graduated from the University of Colorado Boulder, and he has both a background in both earth science and computer science. His main work is on the interactions of meltwater on snow, which led to the discovery of a new meltwater mechanism, which occurs over Greenland and can lead to the rapid acceleration of runoff. And these are low permeability ice slabs. I think that many of you have probably heard me talk about this. The paper that he wrote has been very influential to many of us who study Fern, in both from the perspective of the atmosphere, as well as on the impacts of sea level rise in the future. So just some other information that's probably good for iHARP in particular is he also has a specialty in computer vision and machine learning technologies. And he has a distinction of having worked with in situ data collection in the field, as well as remote sensing data and airborne on observations. So he's kind of done it all. And with that, I'll turn it over to Mike and let him speak for himself. I can't hear you.
Okay, is that better?
Much better.
All right,
Great.
sorry, it grabbed my wrong microphone. All right, okay, so hello, thank you, Tree, for the intro, and I will just hop on here. Let me start my presentation, because I know we have limited time. Just a second. All right, and then I'll share my screen here. Get that PowerPoint. Share. All right, are you all seeing the presentation?
I am.
Yes. All right, great. So as Tree noted, first of all, nice to meet many of you. Some of you I've known before. As Tree noted, my background has been in glaciology, but before that, my master's was in computer science and my undergrad was in computer engineering. So I do come from a computing background into earth sciences. And through my PhD, I spent a fair amount of time on the Greenland ice sheet. And my talk is about emerging hydrologic feats, not all of which is my work, by the way, but on the Greenland ice sheet and some of the things we know, what we don't know, and some of the big questions, because it's actually been a pretty exciting time to be a Greenland ice sheet hydrology person over the last 10 years or so. And so to take a little step back, we have evidence from paleo records that there was a recent paper out about they had taken sub-ice samples of the bedrock stratigraphy from the Camp Century ice core, which was actually drilled in 1963, but they hadn't done anything with the bedrock sediments until just recently. And they found that just due to the paleo records buried deep in the ice sheet, and Camp Century is fairly high up in the ice. It's not in the middle, but it's at about 1,700 meters elevation up in the ice sheet. That from the Camp Century records, there's been at least 2 episodes of ice vegetated conditions followed by glaciation at the Camp Century site, which tells us that in the fairly recent past, several tens of thousands of years, that Greenland has lost considerable amounts of ice. And another paper that was out a couple of years ago was a modeling study looking out to the year 3000, showing that under different climate scenarios, RCP 2.6, 4.5, 8.5, sort of the low emissions, middle, high emissions scenarios, that Greenland could potentially by the year 3000 be ice-free. But the big question, of course, for humanity's sake is how much, how fast, how quickly could Greenland ice go? Could it happen faster than 1,000 years? And those are the kinds of feedbacks we're looking at to try and help answer these questions. So a bit of background in ice sheet hydrology. In the early 60s, the Army Corps of Engineers, during the Cold War, with a lot of money being dumped into polar studies, primarily to defend against Russia. They were doing a lot of studies in Greenland. And over the course of 4 years, they did a very large traverse starting up at Thule Air Base up in the northwest edge of Greenland, and then into the middle of the ice sheet. And the entire time they were digging huge snow pits, taking ice cores, and just doing surveys of the ice sheet to learn about the way that ice sheets worked. And they generated these maps of what we call the facies of the ice sheet. So in the edge of the ice sheet, down where it's warm in the summer, as we get the bare ice zone, where it melts away all the summer snow and then runs off in the winter, and then up to the dry snow zone up high. It's where it never gets warm enough to really melt the snow. You just get snow buried year after year, and then you get these sort of wet facies in between where some of the water melts and percolates down and refreezes into these ice lenses throughout the firn. And they came up with the first basic map, and a lot of this was extrapolated. They hadn't seen the entire ice sheet, but the map over Greenland of where these zones lay on the Greenland ice sheet. And this was in the early 60s. A lot of the traverses were done in the late 50s. And this was back in the days when you could have 100 people working on a project and one author on the paper. It's kind of the opposite now, where you got one person doing most of the work and then 15 authors on the paper. Not saying one's better than the other, they're just very different. Anyways, this is sort of the early sort of maps of like, all right, here's the bits of how hydrology works on the Greenland ice sheet. About 10 traverse by Rick Forster and others in southeast Greenland at this time, where they were drilling cores in late winter. Like this was late March, and it had been a cold winter. It was well below freezing, hadn't been above freezing for months and months. And after they got about 10 meters down into the firn, they started pulling up. They were trying to pull up firn cores to do surveys along their traverse, and they started pulling up liquid water, which was a huge surprise. Nobody expected any liquid water down there. This was the end of winter. Everything should be frozen solid. And what they just discovered in Greenland was the existence of what we now call Greenland perennial fern aquifers, which are areas that water will percolate down, and rather than refreezing, it's warmed up the firn underneath enough to where water can just reside there in aquifers, porous aquifers under the ice surface. This was the first time people had seen this in mountain glaciers before, but never on an ice sheet. And this was quite a surprise to a number of people, to a whole lot of people, that this had just been there, and nobody knew it was there. It's hard to see. I mean, because you can't survey it from the surface. It's only by doing surveys under the surface that you can really tell this. They knew that if there is water under the surface, they should be able to see it in radar records. So ice penetrating radar. This is from a paper by Clement Miege that showing these radar signals. So we've got two different radar layers. This is both from NASA's Operation Icebridge, which flew from between the IceSat-1 and IceSat-2 missions. Its primary instrument was an altimeter, a laser altimeter, getting ice sheet surface height, but it also had a number of radars on it, different frequencies. The AR is the accumulation radar that gives you sort of a mid-frequency radar, gives you good layering in the snow and ice down to about 30 to 50 meters depth, perhaps deeper, depending what you're looking for. And then the MCORDS radar, the McCord's radar, is a much deeper scanning, longer wavelength radar they use to image the ice bed. And in these images, you actually see this sort of bright reflection from a water table, some 10 to 20 meters under the ice, under the snow surface. And where you see that water table when they're looking for the bed, that basically disappears because the radar signal hits the water, gets a bright reflection off the water, but can't really penetrate through the water, so your bedrock just disappears. And so they used all these surveys from Operation Icebridge to map out where they could detect where these aquifers sit in the Greenland ice sheet. And they're primarily concentrated in southeast Greenland. This is where you get extremely high accumulation rates. A lot of snow comes in from the North Atlantic and pummels that coast with meters and meters of snow every year. And that's enough to bury the meltwater so that it does not refreeze from winter cold getting down to it. It basically can insulate the layer enough. And if you get enough meltwater and enough snow, you can start to form these perennial fern aquifers. This was a pretty big discovery. And the biggest paper from it came out in 2014 with Forster that had sort of announced the discovery of these things. Clement Miege had put out these maps in 2016. And it's worth noting that like this, nobody had known this even existed, and it covers roughly 5% of the ice sheet. And nobody knew these existed until about 10 years ago. Around that same time, or actually, yeah, let me take a half step back before I continue on with the story. But some of the questions are, all right, so there's aquifers that can form. And we know in the other areas of the ice sheet, like where Benson in the 60s had surveyed, we get all these little ice lenses forming. But in a steady state climate, you can sort of assume those zones stay the same. There's aquifers where there's aquifers, there's ice lenses where there's ice lenses. But what if we start changing the fern, start adding more melt? And that's what we're doing. We're running a big global experiment right now. There was a paper out in 2012 by Joel Harper that showed they did some surveys of meltwater percolation zone in West Greenland, central West Greenland, along a transect, did some fern cores and set some thermistor strings where they can actually measure the percolation of meltwater and refreezing and its temperature signal in the ice as that's happening, as it's warming the fern down as water's getting deeper into it. And they determined that meltwater can actually get quite deep and that you could probably fill up the fern before you really started seeing runoff from high in the ice. I was sort of trying to answer the question of how long would it take before more melt that was occurring on top of fern would really result in more runoff. And they said they found, given how much fern there is, it would take decades at least required to fill this pore space that had been accumulating for hundreds of years under a range of plausible climate conditions before you would actually start causing runoff. And the order of 20, 30, 50 years, depending where you are in Greenland. So this was kind of it came out in Nature. It was sort of like timeout. This could take longer. This is actually a buffer here mechanism, and this could take a lot longer to fill up the fern than anticipated, which is good news for, sea level. Around that same time, I was actually a PhD student and on my first campaign to Greenland. And we went up to Canyu. It was an area in the percolation zone where we knew there had been a lot of melt in recent years. 2010 had been a big melt summer there. We were there in May of 2012. And we were there to do a number of things, but I was with a team and we were drilling fern cores as one does when they want to see what's going on in the fern. And so there I am with a really heavy fern core drill. And this is kind of what we were expecting to find is a lot of these, this is a fern core laid out on the snow with a lot of these little melt layers scattered in it. Meltwater will percolate down and then sort of flatten out into a lens and refreeze like this in the fern. What we ended up finding though, when we got about a meter or two under the surface was core after core after core of solid ice. And we drilled straight through about 3 to 5 meters of solid ice before hitting patches of fern again, these sort of blue spans or the ice lenses we saw there. And this was really much more than a lens. You think of a lens as something like what's pictured here, maybe anywhere from a couple of centimeters thick up to maybe 10 centimeters thick. But we were drilling through meters and meters of ice just under the surface, like a meter down under the snow. We were there on top of the winter snow and finding all this ice under there. And it really got us thinking as we were there. We drilled several cores at different sites. We took some radar data and just everywhere we looked, we saw these big, huge, thick layers right under the surface. And I remember one distinctly warm day, we were sitting out waiting for a plane to pick us up. This was at our end of our campaign. And we were wondering like, well, geez, with all this ice underneath there, like how many more big melt years would it take before the water's just got nowhere else to go? If you're filling it up with ice, and you would start running off. We really didn't know the answer to that question, but we got an answer pretty quickly. We were there in May 2012. July 2012 saw the biggest melt event in recorded history at Greenland. Twice it had melted all the way up to summit camp in July 12th. It in fact was for the first time in at least 160 years. It was melting across the entire Greenland ice sheet on that day. And this was a pretty big event. There was huge amounts of runoff, not only just melt at summit camp where it melted some 10 centimeters, but at Canyu, that spot where we had been. This was actually an image from mid-July around the time of the peak melt that we saw these slush fields. This is a Landsat 7 these slush fields coming directly from where we had been camped at Canyon and running off westward towards the coast. So we knew that, well, we got our answer real quick to how many more big melt summers it would take before we started seeing runoff from Canyon. Nobody had seen it this high on the ice sheet in Western Greenland before, meltwater running off to the coast. And it had a big effect on the amount of runoff at the coast. I mean, this is the Watson River in Western Greenland, which is the actual outlet drainage of the ice sheet, the river that drains the ice sheet from the glacier we were on at Canyon. And this is it in May 2012 when things are still fairly frozen up in the ice sheet. But that July 2012, I'll apologize for the choppy video here. It did in fact wash out a bridge and wash a tractor off the bridge. And glaciologists know this video well. It gets overplayed a lot, but it was the biggest runoff that anybody'd seen on the Greenland ice sheet. That bridge had been there for 50 years and the water never touched it before. And so what we realized we were seeing is I'll give a little overview actually of sort of the background of what we were seeing with these ice slabs. Up in the dry snow zones, as I explained before, it's high and dry in the ice sheet. Snow accumulates year after year and forms all these layers that you drill for in ice cores, for instance. In the ablation zone, it still gets snow every winter, but in the summer, it gets warm enough to melt away all the snow and it runs off towards the edge of the ice sheet. And this happens every year, feeds the rivers around Greenland. Nothing unusual about that. But in the middle, it's the biggest region of the ice sheet these days is the percolation zone. And this is an area where you get the winter snow, same as everywhere else, but then in the summer, it partially melts away, refreezes into these ice lenses. And then the next year you get more snow on top and you just sort of get these firn layers that have these ice lenses scattered throughout. This is what Benson was surveying in the 60s. But the problem is when you start to increase that melt, you get more and more of these layers. You get a more crowded firn layer in the top. And then eventually, if you get enough years of this, you start to anneal and freeze all these together into what we've determined, what we started calling ice slabs, these meters thick layers that if you get those thick enough and continuous enough, and then it doesn't matter how much pore space is underneath. You can start running off right off the top of these. And this is what we saw happening at Canyon that summer of 2012, just a couple of months after we drilled through these things. It was running off right over the top of them. We estimated that summer in Western Greenland, those ice slabs high in the ice had contributed about an extra 11%, give or take, to the total runoff. It still would have been a huge record-breaking melt year in Greenland and runoff year in Western Greenland, even without those ice slabs, but it was contributing to the area that was running off and contributing to the total volumes of meltwater running off from the ice sheet. So we knew we had a pretty big story, but we only had data at Canyon, where we drilled a few cores. We got really lucky with being able to divert some funding the following year in 2013 and actually do a much wider survey of these things. We got to do a large snowmobile traverse with ice penetrating radar, which you kind of see along a 45-kilometer stretch of radar that we'd collected over a number of days away from our camp. And we chose that specific line, even though it went a few kilometers south of Canyon, primarily because it underflew an overflight line from the Ice Bridge radar. NASA's Operation Ice Bridge was still running, so we wanted to link up our in situ radar with the radar from Ice Bridge, and we also drilled cores all along this radar line to determine where these ice lenses were. And so you can tell just from looking at these pictures that obviously I can see the same really thick lenses. Obviously, you get a lot more detail in the on the ground in situ radar than we do in the airborne radar, but you still, the thickest of these lenses, you can see them. Turns out that actually automating picking these things out was a non-trivial task. It was sort of the bane of the third chapter of my PhD, second chapter of my PhD. This top figure here is sort of what you see from an Operation Ice Bridge file when you download it from NSIDC. It's an undulating surface. You get radar echoes in the signals. A lot of these are actually caused by the aircraft wings, can echo the signal back and forth from the surface, or from the fuselages. There can be radar interference that happens, and then it tells you what where it thinks the surface is, that it's sort of auto-picked, and this is what you're seeing in B, like the 0 line here is where it thinks the surface is, but obviously it's getting it wrong sometimes. These dark areas are these ice slabs I'm trying to pick out. And so first thing I had to do is run through the entire set of radar data everywhere they flew over Greenland and improve the surface picking so that I could get a surface, and that's what first thing I did. It took about 6 different iterations of algorithms to get it working well enough for my purposes. And then from there, I had to do things like remove lakes. There are a number of areas where, similar to the aquifers, there's actually lakes that form on the ice that don't drain during the summer, and so that stay liquid during the winter and just get covered in ice, but they're still liquid. Every time the flight went over one of these, you'd see these huge reflection, and then everything extincted beneath, just like the aquifers. Had to mask out a bunch of those. These lakes were in fact documented by Laura Koenig and others in a 2015 paper. I had to remove 150 of those, 130 of those from the flight lines. The aircraft radar gets much weaker anytime the plane is turning, simply because it's no longer pointing straight down at nadir and onto the snow surface. I had to do some. A lot of times people just mask these out. Anywhere it's the plane is turning, you just say don't use that data. But I was doing a correction for the roll to try and improve the signal where it had gotten weaker from aircraft roll. And then do again with depth correction, because even though the initial radar processing homogenized the signal somewhat, it would still get weaker the deeper you went. And I needed this normalized, so had to do a depth correction flight line by flight line. And unfortunately, I couldn't just do the exact same calculations for all the data set, because they slightly changed the instruments and changed the aircraft it's on from one year to the next. So 1 year's set of radar data would not necessarily be the same as the next year's data set. So it was really file by file I was needing to do this. I automated it all as best I could, but it was highly supervised as I was doing it. And then I needed to pick out where ice slabs were, trying to match up this stuff that we were seeing in the in situ radar. And so I was using empirical thresholds to get it to the closest along that flight line of what we could see in the in situ radar, and then some denoising, some thresholding and denoising to get my eventual pick of, I'm not going to say these are perfect maps, but this is the best we can do in mapping out where ice slabs are in the firn from ice bridge radar. And doing that with all the layers we had over Greenland, we were able to map out where in Greenland these low permeability ice slabs existed, and the approximate thickness of them where they were. And this came out in a paper a few years ago now, in 2019, mapping out ice slabs in Greenland. This was the first such map that had been produced. And just a little zoom in on a couple of areas that are of particular interest. A lot of our focus was in southwest Greenland down here, but there's actually a large area of very shallow or low-lying ice and fairly warm area in northeast Greenland that also has a considerable amount of these things. They cover already about 5% of the Greenland ice sheet, similar to the area of the aquifers that were discovered. Lakes do form on top of them, and we know that they enhance runoff in warm years. We had done some rough calculations for the year 2012 in one area of Greenland, but exactly how much they're enhancing runoff in Greenland is still an open question. We don't know for sure, in part because these ice slabs don't necessarily run off 100% of the water. A little bit of water can sometimes get through them. Sometimes lakes can drain through them, which I'll get into in just a bit. But there's still a lot of open questions about these. But I had taken where I'd mapped the ice slabs and then did some runs with climate models, with regional climate models like RACMO and HIRHAM and MAR, which are some of the regional climate models that simulate ice sheet surface mass balance. And so I first took these different model outputs that we had. Sorry, these aren't labeled. I don't have the full caption here, but and tried to simulate when, all of them showed that melt really started increasing, and the area where these ice slabs would form really started increasing in late 2000. 2002 had a large record-breaking melt year in Greenland, and then a number of them since had really increased the area where these ice slabs fit. This was sort of the historical up through 2014 observations. And then I looked out to 2100 under different scenarios, RCP 4.5 and 8.5, to simulate using those same sort of boxes around the forcings. How much accumulation and how much melt does it take to form these ice slabs where they currently sit? And then with that same box around the parameters, where would we expect ice slabs to be forming into the future? And some of these sort of more severe scenarios, it's hard to necessarily look at the most severe one and say, well, that's what's going to happen. But this sort of span of what's happened so far is hitting the upper end of what these RCM simulations simulate. So I would actually argue that like this green line is probably unrealistic. It shows by 2100 we would have as many ice slabs as we do right now already. So I'd probably toss out some of the lower ones here as unrealistic, and it's hard to say where in these more severe ones we would sit. A lot of that obviously depends on humanity's choices for the climate in the coming century here. So yeah, some things we know about ice slabs. They are growing thicker. It doesn't, once they start forming, this was actually repeat cores we had drilled on repeat visits back to the CanU site where we'd first discovered them in 2012. And there was actually a team there in 2019 that had only drilled a few meters down, so there might have been more ice underneath it. But we do see just over time, in general, that they're getting thicker. They started out a couple of layers anywhere from 3 to 5 meters thick, and then they're upwards of 7 meters thick or more in 2017 when we're drilling in the same spots. Now, there is a lot of noise in individual drill sites, but when you see that trend over a series of years, you start to believe it. It's hard to compare just two cores individually because just spatial variability from one to the next. But with enough cores, you start to get data showing that like these things are thickening up. And the thicker they get, the harder it is for water to get through them, and the more easily it can cap off the firn layer and run off. Coming back to the aquifers, this is areas where aquifers had been those perennial fern aquifers. I did some simulations around with the same RCMs around where the aquifers sit compared to where ice slabs sit. And so I've got colored here, the purple is areas where these perennial fern aquifers, according to the simulation, where those are based on the climate model forcings. And then the dark blue is where the ice slabs currently are, according to the climate model forcings. These aren't perfect maps. These are sort of simple boxes put around the outputs of regional climate models. Simple parameter boxes saying, all right, under this set of forcing conditions, we would expect ice slabs to be there. Under the other set, we would expect aquifers to be there. That's in 2014. If you look out to 2100, these have both greatly expanded. We don't yet have enough evidence to really show whether or not aquifers have been expanding. We don't really know, but you would expect in areas with enough accumulation, if you start ramping up melt enough, that you would start to form aquifers at higher and higher elevations. We already know that if you have a low enough accumulation and high enough melt, you start to form ice slabs. So if you get more and more melt higher on the ice sheet, you get much larger ice slabs. To me, these are scary pictures. Like these are huge areas of ice that would be running off. I mean, this area down here near the coast is where you would expect runoff to normally occur, and you've more than doubled the size of the runoff zone by 2100. This is under RCP 8.5. Again, it's hard to say that future will go that route. This isn't even the most sensitive of the models, though. Under the CanESM, that's the most sensitive of the MAR model runs. You get even more severe maps. In these areas where like aquifers and ice slabs bump up right against each other, we have no idea what's really going on with the subsurface hydrology there. And that there do exist areas currently where those two areas bump right up against each other, and nobody's surveyed there. I'd put in a proposal to do that and didn't get funded because things don't always get funded. We do know that both, or at least ice slabs, but potentially aquifers as well, are influenced by these huge melt summers we get. 2012 was this big record-breaking one. We had a very large melt summer in 2019, another one in 2021. These are happening more often than they used to. In 2013, Dan McGrath had a small paper out in GRL about basically just looking at trends in temperatures at Summit Camp Greenland at the weather station that Coney Stephan at the time, had been maintaining there for several decades. And based on weather station trends, so this is just taking trends line of temperatures and extrapolating into the future and seeing based on variability from year to year, what the maximum temperature has got to, you could start to get probabilities of how often it would melt there in the future. And he predicted that by 2025, this was now 3 years from now, that there'd be a 50% probability of the Greenland ice sheet's dry snow zone essentially disappearing, turning into a percolation facies, where you get, and he defined percolation facies at the time as getting melt at least once every other year. Like in 50% of years, you're getting melt, and so therefore forming ice lenses in the firn. This would be a very dramatic transformation in the span of 20 to 30 years to completely disappear Greenland's dry snow zone. I'm not sure he's wrong yet. I mean, it might take some time after 2025 to see if we actually hit a 50% probability if we're really getting melt all the way up to summit every other year or not, but we're not that far off it right now. So it's hard to say yet that like, oh no, that's not going to happen in 3 years. Like, it might. So this is just food for thought. But it's very large, dramatic changes happening in Greenland melt and runoff and all these things we're seeing on the subsurface fern. Some just other looks at the ice slabs and the aquifers. This is the two maps from two different papers of where these things sit using two different methodologies completely. We'd analyze the same radar, but in very different ways. My map's on the left of the ice slabs, and Clement's map is on the right with the aquifers. If you put those together, you don't have to squint back and forth between them. You do get this sort of, some areas of Greenland get aquifers and other areas get ice slabs. And we already know that the big dividing line between them is mean snow accumulation. So how much snow do you get a year? In areas of really high accumulation where a lot of storm tracks pummel the coast all winter with heavy snowfall, you get these huge aquifer areas, and then in lower accumulation zones where you don't get as much insulation from winter snow, if you get enough melt, you'll start to form ice slabs. We know that basically. It's not a perfect picture. There are, if I zoom back, there are some of these spots where we get little bits that it turns out aren't really aquifers actually. There's some new work coming out soon I'll touch upon it in a little bit, but there's some other weird things going on that appear that are liquid water under the surface, but not necessarily aquifers per se. And the runoff patterns from these two zones are very, very different. This is just sort of an idealized cartoon picture, but I mean, from an ice slab, it freezes up solid in the winter. You get no runoff in the winter. In the summer, you'll get this huge pulse of runoff if you get a warm melt season where you're just getting tremendous amounts of runoff to the coast, and then it freezes back up in the fall. Whereas aquifers can drain potentially any time of year. There has been, Kristen Pointer had a paper out about 4 years ago now, 5 years, where they had discovered on a plane flying over crevasses in southeast Greenland that there was in fact water draining from an aquifer straight into a crevasse under the surface. You could only see it from flying over the crevasse and seeing literally water draining off the side of the ice wall into the crevasse. So potentially you could have runoff of some form into a crevasse from an aquifer any time of year, but you would assume as you're getting more meltwater inputs from the surface in the summer that it would increase in the summer. Truth is, we don't know though. I'm just making these up. Like this is idealized. Like we don't actually know from an aquifer how the runoff patterns go. That's an open question. One thing that really surprised me, this is in midsummer 2012 during that big record-breaking melt season. We had just a few months earlier been there on the ice sheet, drilling cores and discovering these big thick ice slabs that were then having runoff over the top of them. This is a high resolution worldview imagery. This is these half-meter commercial satellite images. There's nothing that surprising other than this is just a kind of a beautiful black and white picture of these slush fields forming into runoff channels, funneling off downhill to the west. Except when I start to zoom in on these pictures, I started seeing all these lines in the fern, which surprised. First, I thought, well, that's just got to be a satellite striping error. But then as I zoomed around the image, I'm like, no, those are cracks in the surface. which surprised us because we'd been driving over these things by the time we discovered this picture for several years already and never knew they were there. There really shouldn't be crevasses this high on the ice. And if I look at different areas, some of the crevasses were water filled, but there were cracks all over this picture. And the previous research had shown, well, actually research right around that time in 2015 when I was looking at that picture, was showing that that crevasses shouldn't happen really high in Greenland. There was a big question. Okay, we know that lakes are forming higher and higher on the ice, and we know that lakes can drain, which I'll get into in just a little bit. Lakes can drain on the ice, but we don't yet really know. Like, in order for lakes to drain, they pretty much need to hit a crevasse. And so there was a paper out saying, all right, well, the ice moves really slow in the high areas of the ice sheet. We found that the upper limit to where crevasses and therefore moulins are likely to form is about 1,600 meters elevation in Western Greenland. Like, all right, no crevasses, but can use it 1,860. We see crevasses there. Like, what's going on? I'm realizing I'm running out of time here, so I'm going to need to. I'm going to fly through some of the rest of these things, but I had an undergrad intern to go through and hand digitize all the crevasses we could see in that worldview image. There's hundreds of them there. So there's definitely crevasses up high. And we care about them because of the fact that they can drain water to the bed of an ice sheet. It's a process called hydrofracture. If you get a narrow crevasse, which most crevasses are, these thin, narrow features in the ice, and you fill it with water, which is heavier than snow, heavier than ice, can create enough hydraulic head to actually split a crack open where the force of the water against the wall is greater than the force of the ice pushing back against the water. It can actually split the ice straight down to the bed through kilometers of ice. And if you get enough hydraulic head on the top of it. And that can, in fact, then drain an entire lake, for instance, all the way to the bed of the ice sheet. And this was sort of this was a little animation showing what could happen to the ice. This was after a paper in 2002 when they'd set up GPSs, and after lake drainages, they saw some speed ups of the ice, and they hypothesized that these lake drainages were actually lubricating the ice underneath it and causing speed ups in velocity of the ice. It turns out it's not that simple of a story. Other research had followed up years later, showing that yes, you do get a big speed up in ice from a lake drainage event, but it doesn't necessarily sustain itself through the summer. These lake drainage events to the bed of the ice sheet also carve out conduits, these subglacial drainages underneath the ice sheet. And when you get an efficient drainage system underneath the ice, it's no longer really lubricating it. You actually see a slowdown in warmer years after the big speed up, whereas in cooler years, when you don't get quite as much melted, it can stay elevated speeds for longer, and you actually don't. It can be the net effect on ice velocity is negligible or perhaps even negative, depending. So it may not be that big of a story, but these are relatively low elevation ice, 1,000 meters or lower, but high on the ice sheet in places like Canyu. If you get lake drainages that high, there is not nearly as well developed of subglacial channels, and there's much higher pressure underneath the ice, just due to the fact you got twice as much ice on top of it. And basically, drainage at high elevations would actually cause a bigger problem, potentially more speed up than at lower elevations. And we've seen that. There's a remote sensing survey out Sarah Cooley had done, and showing that high elevation lakes are actually just as likely to drain as low elevation lakes. We think it's because of these high elevation crevasses that are forming. And so this then, sort of begs the questions. Like, most of Greenland's ice is pretty thick stuff. This is, ice thickness measurements from Matthew's bed machine product, and then ice velocities from some of the NASA data sets. A lot of attention in glaciology gets paid to these really fast moving outlet glaciers, but the vast majority of Greenland's ice on the interior is moving pretty darn slow. It's slow, thick, boring ice. The ice dynamics people who study ice movement don't pay much attention to it because it's not doing interesting things. It's just slowly moving, creeping year out to the coast. In this blue area that I've highlighted, this is basically combining these two masks, is ice that's 1,500 meters thick or thicker and moving less than 100 meters a year. It's the thick, slow boring ice. It's 56% of the ice area. It's over 84% of the ice volume. It's most of Greenland is this big, thick, slow boring ice. CanU is sort of at the outer edge of this thick, slow boring ice. And so it begs the question, if you're draining lakes high up on the ice, what potential does that have to start waking up the big, slow, thick, boring ice? We don't know. It's an open question. Just like the initial papers that said, oh, well, lake drainages will speed up the ice. And then it's like, well, hold on, there's some feedbacks going on in there. Like we actually don't know the net effect if you start having lake drainages higher and higher. But it's questions that need answering. I tried to do some of this. And this is a fact from a proposal I'd written that wasn't funded, womp womp. But on trying to study this a bit more, where we saw like a lake way up at near CanU that did in fact drain, and it did not, unlike this lake, which just sort of overflowed its basin and then slowly ran downhill. This one had nowhere to go. The water just disappeared. So we know lakes are draining up high. And I'd done a survey with ice velocities. NASA has an ice velocity data set that they get from repeat Landsat images where they can pick out ice velocities. And in the interior of Greenland, it's hard to get really good data, but I showed that over the 7-year span of data that we had, in the area where ice slabs were, where there's lakes that are forming on top of these ice slabs and some of them draining, that there is a ever so slight average increase in ice velocity of about 13 centimeters a year per year, but that it was dwarfed by the uncertainty in the measurements. There's a wide range of measurements, plus or minus, 1.9 meters per year, not statistically significant. So the answer is we don't really know yet if lake drainages, if ice velocities are speeding up at all on the big, slow boring ice of Greenland, and if so, by how much, and if they are, if lake drainages are playing a part in that. We don't know. It's tempting to think, well, maybe, but we don't know. There maybe could be some smart work done with some of this data to see if we could tease something like that out. I am out of time, but I'm just about done here. Unfortunately, monitoring these ice slabs and these aquifers, it was all done with IceBridge radar. IceBridge is now done. IceSat-2 has been flying for a few years. IceBridge is no longer needed, so we don't have ground penetrating radar to keep doing these surveys over Greenland. But Julie Miller has had some recent success with passive microwave algorithms on picking out both ice slabs and aquifers. It's noisy. These aren't perfect yet. This isn't a perfect match between these two data sets. And I apologize, the color schemes are like totally backwards between these two images. But there's at least some initial results that potentially with microwave sounding and or passive microwave signals, we can get fern aquifers and ice slabs exist in Greenland, and then we could monitor them for the foreseeable future. So that's promising, because then we can start mapping out where these things are changing. So I guess in summary, things we know about, things that we have discovered recently in the last 10 years or so about ice sheet hydrology in Greenland, that both ice slabs and aquifers exist, and they play major components in Greenland's fern hydrology. Both were discovered in polar ice sheets about 10 years ago in Greenland. They do exist in Antarctica to some extent, although less so. Most of Antarctica is dry snow zone. They can cause drainage into crevasses, which may, in big emphasis on may or may not, affect ice dynamics. Ice slabs are increasing runoff in large melt years. Ice slabs do form lakes atop them, which can drain. And they're growing, at least the ice slabs. We don't know if the aquifers are growing. I suspect they may be, but I don't know. And we can presumably monitor, there's some early work here now monitoring both ice slabs and aquifers with remote sensing data. Things we don't know is how fast these ice slabs or aquifers are changing. These radar pictures that we had gotten from all these repeat IceBridge flights basically painted a snapshot over this 5-year period, over this 7-year period where IceBridge was collected. This is where we see them. There really hasn't been any change analysis done on these subsurface layers comprehensively across the ice sheet. That is an open question. And as to how these are changing in different melt years. Part of the issues with doing change analysis is a lot of these flight lines weren't repeated. They were flown once. A lot of it was doing things like mapping bedrock, for instance, so you don't need to fly an flight line twice. So there's a very limited number of repeat overflights. There are some areas, though, they did fly continuously year after year. We don't yet really know the exact effects of atmospheric warming and circulation changes are having on these changes in firn hydrology. Given that we don't know all the changes in firn hydrology to start with, it's hard to then map atmospheric effects on firn hydrology. The work I'd done with the ice slabs was really just very simply saying, all right, here were the conditions where ice slabs had formed based on what the regional climate models are saying. But that does not necessarily draw an exact cause and effect relationship. We don't really know if or how water patterns are changing as a result of these sort of newly discovered and potentially changing facies in the ice sheet. We don't know if ice slab lake drainages are reaching the bed or not. There's some work being done by a grad student, I think he's finishing up now, out of Stanford, that his name was on the tip of my tongue, and now Riley Kohlberg out of Stanford that is showing some areas where lakes have drained, where water will actually fill up the firn for a couple of years before refreezing. It ends up looking like a tiny aquifer there in the radar, but he's called them ice blobs that form underneath these ice slabs. But then if you fill up an ice blob, then if you get another ice drainage there in a subsequent year, then does it go through that blob and then get through the rest of the ice? We don't know. There's a lot we could potentially pick out in the radar that may help answer some of these questions. The work just hasn't been done or funded. So, and then one of the big questions in my mind is if the thick, boring ice in Greenland is starting to respond or not to increased meltwater. Inconclusive as of yet. So, at least from a Greenland hydrology perspective, that's what I've got. Sorry I went over time, but I'm done talking for now.
Thank you very much, Mike. I'm really impressed with your ability to talk faster and faster as we run out of time. So with that, we have 10 minutes left. I'm going to moderate questions. And so I'm seeing some members of my team, and I'm going to ignore you and point out people who... Okay, Jianwu, please go ahead.
This is Jian Wu from UMBC. I'm a background in data science. So it's what you said. It's very new to me. I'm trying to learn the terminologies you are talking about. I think in the last slide you have a good summary of the things you don't know. Because iHARP is an interdisciplinary research institute, so we want to know from you, especially for you, because you have background both in computer science and the ice. So from your perspective, how this interdisciplinary kind of efforts research could help you answer some of the questions, and in the first important question you want to get answered, and also something what other questions that could help by data science. Thanks.
So yeah, I mean, absolutely. Thank you, Jianwu. So there's a lot of big data sets out there that have only had sort of the most rudimentary analyses done on them, mapping data sets. So there's been a lot of work in things like Google Earth Engine on like mapping where lakes show up and sometimes rivers where you can see them on the surface. And some work on like lake drainages and things like that. But there are a lot of layers of data, including these radar layers. Like I've said, there's a lot of things in the radar that I was just trying to pick out ice slabs, and Clement Mead was just trying to pick out aquifers, and it was just that. But there's a lot more data in there and features in there that we haven't really mapped out, and we haven't done in a very comprehensive way. And actually, nobody's done yet over Antarctica to see if we can pick out either of these features down. I take that back. Some of the aquifer work has been done over Antarctica, but taking a more data science driven approach to some of these data sets, these are fairly large quantities of data, could tease out some things that were just missed in sort of the more manual approaches that were being taken before. And especially when you start to pull in very large remotely sensed data sets, when you start to lay over ice velocities on top of it, and you start to lay over, changes in these ice slab features, areas where lakes drain, areas where we have, where we're measuring velocities, where changes in those are happening, and start to tease out patterns that maybe we had missed before. I don't know. There's There's just a whole lot of different data sets we can throw of this, all of which are very imperfect in their own right and have their own errors and have their own uncertainties. But when we put them all together, we may be able to tease out some really interesting answers. Perhaps some answers to the questions I put up on what we don't know, but perhaps some others. And I'm not sure what all those are yet. That's a very vague answer to that question, but there's just a lot that hasn't been done with this data that I think, I can hand over what I did with the ice bridge radar and be like, all right, well, here's what we see. And I could go over it with people and be like, all right, what are there any trends we can pick out? Are there any things like that? But that's just one data set, and there's so many of these data sets. So been a lot of data collection. There's been, I think, not nearly as much analysis on the data as could be done. So that's what y'all are here to do. So
Well,
Yeah,
that's what
good
you're
to
here
know.
to do too,
Thanks.
buddy. It's so any other questions? If you can raise your hand on, okay. Karen, please.
Hi, I'm a data scientist too. I'm pretty ignorant about the glaciology, but thank you for the introduction. So, my question a bit matter, in machine learning, we really rely on the feedback loop, right? So if you get wrong, and then we have a feedback loop, and then we can self-correcting in some sense.
Mhm.
So in your field, I'm not talking about the feedback loop of the hydrology. I'm talking about
Right.
the feedback loop. How do we know that our model is not doing well? We cannot wait for like a 10 years or 100 years to check that, right? So what's the mechanism for you to know that? Or maybe you do like a triangulation. I think you mentioned that radar or maybe have different sensor, did it get different kind of measurement from different perspective. Of course, we talk about different things. One is the measurement and nowcasting to figure out what's going on now, right? But we're also talking about the model to predict the future,
Sure.
right?
Yeah. Yeah. So I mean, that's definitely a loaded question. Like it in a good way. It's like it's how do we know that the models are doing well or not? And especially if you're going to try and extrapolate out into the future, that's a very dangerous territory to go into if we don't know that we have all the cause and effect exactly right for the present. And I mean, in terms of how we've done it, like I'm always a big fan of having an independent validation data set, which is either, a slice of the data we have that we set aside that we have already manually tagged that we can then use as test and validation, which is a pretty common thing in machine learning, obviously, as I don't have to tell you guys. But I mean, for instance, or just an entirely different data set that can give us some measure of what we're looking for and see if our answers line up with what this other data set says. I mean, like when I was running, my analysis of the ice bridge or the ice bridge radar and picking out layers in there of where these big ice slabs where we can see them, I kept taking it back to where we had cores, anywhere I would try and run the analysis, and automate where we were in empirical thresholds as to where what was or was not ice slabs in the data, and then bring it back to anywhere we had cores, like how well does it fit the cores. And so, I mean, that's, I wish we had hundreds and hundreds of cores. It'd been a lot better if we did, but, cores are expensive to get. I'm not giving a very good answer to your question at all right now, but it's hard. I mean, and this is definitely obvious. I don't have to tell you, but obviously if we, are wanting to take machine learning approaches to any of these kinds of questions to answer them, you're going to have to really think through how we're going to get the validation and how we know we're getting it right versus just completely going off the wall on what may or may not really be happening. I mean, it's hard to really give a firm answer to that question without having a particular problem that we're talking about. So yeah, I don't have a very specific answer to that question, but it's a good question and definitely a very important one. So
What I heard was validation and cross validation. So
yeah.
so I'm seeing no other hands.
There's a question from Shashi in the Q&A.
Oh, I'm sorry.
I can read it
Let me
out.
see. Great.
What are the limitations of current ML in context of analyzing ice sheet data? Is there a need for new ML tools which are not available today?
Ooh, great question. I mean, again, it kind of comes back to which data sets we're looking at. I mean, obviously, some of them lend themselves to machine learning approaches much better than others. And so I have a computer science background, but I am not a machine learning expert. This is where I, definitely lean on the data scientists in the room here to pick out where we're, what sorts of questions and the data sets we have that might best be able to get answered with machine learning approaches. It's very hard for me to say exactly which data sets are going to work best and what we are and aren't going to be able to answer. I realize I'm not really answering your question. I'm floating around it. So
Just say radar. Just say radar.
yeah, right. I mean, we got the radar data, and that has been, sort of using very different techniques, run through different, very much empirical algorithms. Actually, for the aquifer pick, it was actually a consensus, literally, where they had 5 people say, all right, where are their aquifers and where aren't they? And majority won on any given radar flight line. It was expert tagging essentially as to where aquifers were and weren't, which obviously you can use then to train an algorithm. But if we've already done it on all the Icebridge data, then it begs like, all right, what do we then apply it to? But there are other radar data sets out there. I don't know. It's very hard to give some specific answers. These are very, very good questions, but it's very hard to give specific answers to them without having specific data sets and specific applications that we're trying to answer, because the caveats, the devil's in the details, obviously, as we all know. So it's hard to be like, wow, totally, we could take all the velocity data and do X and Y and Z and discover all kinds of new cool stuff. But until we really look at the velocity data and we see where the warts are in it, it's hard to know really.
Vandana, are you seeing questions somewhere that I'm not? I can't hear you.
There's a Q&A link at the bottom. I don't know if you're seeing that or not. Maybe I was seeing it as a host, but that was the only question in there.
Okay.
I did have a question. Can I jump in, or is there something?
Yeah, of course.
I was
don't
trying
see
to hold
anybody else.
off my questions at the end to see if others had. I actually have a bunch of questions, Mike, so maybe I'll follow up as well. But one quick question. You talked about devil in the details. How do you see thickness versus extent versus volume? I've heard like different pieces for different types of studies. Is one more important than others? For example, in studying the first question that you talked about, thickness versus extent versus volume.
Oh, right. So I mean, in terms of, again, it depends exactly what we're looking at. In terms of like ice slabs, for instance, both the extent and the thickness would really be what the things we're after as to where it could cause runoff and where it couldn't. If they're too thin and sporadic, then they wouldn't really cause runoff over large scales. It's a different thing with aquifers. Like the actual volume of water that's there is something that's sort of a key variable for aquifers. It tells you how much water could drain into crevasses. It tells you how much of a water reservoir there is there. It's really the volume of the water. But again, it kind of depends on what applications we're looking at. Is exactly, if we want to see how much water has been buffered in the firn by refreezing, then knowing that the volume of these ice slabs would be kind of key answering that question. But that doesn't tell us how much runoff there has been. And that's one of the key questions, is like how much, at least in the firn areas of Greenland, in these high elevation areas where meltwater has increased, how much has been buffered in the firn versus how much has run off. We get estimates of that from the climate models, from RACMO and MAR and HIRHAM and such, these regional climate models, but we don't really have measurements of that. And so we have some rivers that are gauged around Greenland where we can actually measure the outflow, and there's work being done on that. But yeah, I mean, I guess to get back to your exact questions, I tend to ramble sometimes. I apologize for that. But in terms of the extent and volume, as to what's important depends what questions we're trying to ask, really, and what our main conclusions we're trying to get to. I mean, they're all important depending on what question you're asking, really, I guess is.
Okay, I'm gonna cut you off.
Yeah.
Vandana, if you're okay with it, and we're over time now.
Yes.
So I'm
So
hoping
I can follow
you
up.
guys will have
others.
an opportunity to follow up with them separately. Yeah.
Yeah. I will be
Great, great.
on the project officially soon, I think. So, yeah.
So that'll work. And thank you again very much for joining us, everybody. Thank you for joining us, and we'll see you soon.
All right.
Thanks so much, Mike. Thank
Good to
you.
meet you all. Yeah.
Thank you.
Thank you.
Thanks, Mike.
Bye.
Bye.